With the AOIP, the addressing is, of course, everything in terms of the routing. So you typically need both Ethernet and IP addresses, but the users never actually type in an IP address. The engineers may do some of that in the initial configuration of the system, but typically the users don't. There are either software applications on a PC that make it drag and drop, or that kind of real user friendly, or as we said, the hardware just sort of does it for you. Now remember, in the Ethernet world, there is the so-called MAC address. Has nothing to do with Macintosh. It means media access control. It's the actual hardware address. You've probably seen it. It's those hex numbers, two by two, with either a colon or a dash between them. Every device you get, every piece of hardware, anything that connects to a network, either wireless or wired or wirelessly, has a MAC address. And 48 bits, you can do the math at how many gazillion possibilities that gives you in this hexadecimal notation. So there's plenty. I mean, again, for a large facility, this is plenty. It's way more than you would ever need for a single audio facility, counting all the inputs and the outputs in the whole place. IP, on the other hand, uses a 32-bit IP address, and you've seen those addresses. They're the 3-digit dot, 2-digit dot, 2-digit, so forth. Those are the common IP addresses. Again, those are generated in these systems. Not typically anything you have to deal with in regular usage. And there's a system called the Address Resolution Protocol in the IP world that the IETF has specified that's a way to translate between a physical MAC address and a virtual IP address. And that all happens, again, transparently to the user under the hood. Now, what a lot of folks don't realize is that the Ethernet addresses, those MAC addresses we talked about, there's almost half of them that are reserved for only multicast use. And they're hardly ever used in a regular computer network, because most computer networking is designed as, you're trying to get from one PC to one other location somewhere on the network. You rarely have these things that you want to go to a lot of people at once in real time. So there's plenty of places for that, and you can use them and never have any collision. And remember, some folks like to have one network for everything, both the enterprise, the offices of a radio station, let's say, and all the studios. Probably not a good idea. It's at least better to have a virtual firewall between those, if not a physical network where you just literally, the wires only go to the studios, and then they have a whole separate set of wires and servers for the offices. But you can share them and still have plenty of isolation, especially because you're using all the multicast stuff, and the offices certainly won't be. You may be more familiar with the fact that there's these blocks of addresses, number of blocks of IP addresses that are set aside for various uses. Some for LANs. Anybody that's set up a home network recognizes that last one, that 192.168 ... That is the sort of local, what all the Wi-Fi routers use for all the bases inside, all the locations inside the home's network. The thinking here is kind of like if you had a phone system in your offices and you didn't want everybody in the 1,000 people in your office to literally have to, they didn't all need to have direct access from the outside world. You could save a lot by not having all those numbers be published by the telephone company and just have them in your PBX, and maybe they're only a 3-digit instead of a 4-digit extension. And people can't directly call to that. They have to go through the switchboard and then be switched through. But it saves a lot of space in the telco's environment because they don't need to publish all those numbers. In other words, those numbers aren't all directly accessible from the outside. That's why you see things, with the extension numbers. You call a main number and then you ask for extension or dial internally on the PBX the extension. Well, that's what these are. This 192.168, if it shows up in a browser, you try to go to a site, the router that you hit just ignores it because it knows there is no such place out there, because in fact that address is used countless numbers of times inside LANs. It is not directly accessible to the outside. So just by the very nature of your using these reserved LAN addresses, it makes your network on that level impervious to outside interception, even if one of the computers or more of them actually has an internet connection to it, which some folks advise against. The fact is they can't really get to the address space you're using anyway if you're using these reserved LANs, which you should. And the old enterprise uses the 10.0. You'll see that occasionally as well. So there's plenty of space for just the LAN. And remember, we're just using this in a LAN environment. So most of the switching, as we said, is done in the Ethernet domain. That is layer 2. And because, as we said, it's cheaper, it's easier, and it is still plenty easy to expand at the Ethernet level. In fact, that's the case for most LANs of any use, whether it's audio or enterprise kind of applications. Now, you may have heard some of these terms for the speed of the internet, of the network rather. These are Ethernet terms. We had the old 10 base T back in the old days, 10 megabits. Now about the lowest you see is 100 base T. And it's literally, it should be called 100 base TX because there was an older 100 base T originally, and then pretty soon it was supplanted by the 100 base TX, but everybody still calls it 100 base T. And so that's your 100 megabit per second, pretty much baseline internet, baseline network, Ethernet network that everybody uses today. And it takes 2 pairs of Cat5 typically on a single RJ45, one in each direction. And we'll show you the wiring pinout in a second. And this is used in AOIP as well, particularly at the edge switch area where you have plenty of bandwidth for just a small number of devices. Then you can move up to what's called gigabit Ethernet, more officially called 1000 base T. The T, by the way, is for twisted pair, twisted copper. And that uses 4 pairs in the same cable, usually Cat6, and it can be Cat5e as well. But the point there is it's still the same connector. It's wired differently, but it's still the RJ45 connector. I'll show you both in a moment. There can also be fiber used instead of copper. It's a little more expensive, of course, but has even more capability for bandwidth. Mostly, it's not so much that the bandwidth changes, because you still see it's 100 megabits or a gigabit. It's that it can handle that bandwidth over longer distances. So when you have big facilities, literally physically big facilities, where from one end to the other, or you go between buildings, let's say, with your own private network, that's where the fiber really comes in handy. Or at least in your core node, you might have fiber from your core switch to your edge switches, and then you can have copper from your edge switches to your nodes and devices. By the same token, you can use gigabit in that core path, and then you can live with 100 base T out at the edges. So that's real scalable in that respect. And you can see the path length differences in this column here between these gigabit services, let's say. These are 3 different gigabit networks. Copper handles 100 meters. One mode of fiber with LEDs handles 500 meters. And then you've got the LX that handles 2 kilometers, up to 2 kilometers on single mode fiber. This is one case where single mode is actually better than multi-mode. Everybody thinks, oh, multi's got to be better than single. But what single mode fiber is actually more expensive, and for any of you who've ever studied fiber optics, pretty cool stuff. It uses something called the total internal reflection. The guy that first discovered it did it with a hose with water in it. And he realized that with the right conditions, all the light that you shine down a tube of continuous transparent stuff, whether it's water or fiber, if you do it right, the light keeps bouncing off the edge and stays inside, never comes out, and actually continues to pass through. And a multi-mode fiber has different characteristics in the core versus the edge, and so it's a little leakier. But a single mode fiber is made pretty much uniform from edge to core, which is harder to do, obviously, and because of the the density is different from the edge to the core. And so if you do it right, that means that whole cross section of that fiber can handle all of this and doesn't leak hardly at all. So that's why single mode fiber can carry the same amount of data over longer distances. So you take your pick. Again, there's like a Chinese menu for all the things that you want, and they're all pretty much off the shelf, which is great.